Okay, so here's our review, and we're going to get to your question, Brad. But let's just get to it first. Calculating the pH of strong acid solutions. You don't want to screw up on the easy ones, right? So how would you do this one? Just take the negative log of it, exactly. What about calculating the pH of weak acid solutions? Ice table. You got to know what? What do I have to give you? I have to give you the Ka, right? So you make an ice table.
When do we know to use formalities?
Okay. We're getting there, right? So then you do an ice table. Right? And put 0.23 there and go on. Right? What is the technical difference between 0.23 molar HCN and 0.23 formal HCN? Here's your formality question. It had to do with...
Because it's not always going to be that way unless it's like a strong acid.
Yeah, okay? It's not always going to be that way, Victoria says. So that means 8.23 molar HCN. Well, the aspect you really want to look at from this compound is the cyanide. The cyanide, it's not only tied up in this HCN form. Most of it is, but some of it's also tied up in CN minus. So technically, it's better to write on a bottle 0.23 formal HCN because the cyanide's tied up in more than one form. Okay, but you're right. You don't do that for strong acids. It's always going to be big M because it only has one form. Okay, so it's more of a comprehension, understanding thing than it is a calculation, really.
So, I'm sorry, yes. So what is the answer?
What's the technical difference? So which one should you write?
Formality.
You should write formality, right? Unless you did all this work, this full systematic treatment of equilibrium, right? And you go through and calculate the concentration of cyanide, the concentration of H+. You went down and you calculated all these forms, right? A full systematic treatment of equilibrium. There, and really only there, I think, is where you can use molarity. Because you actually mean the concentration of hydrogen cyanide. Cyanide in this form is that molarity, that concentration. Okay? So that's what the book is kind of driving at. It's more of a terminology type of idea. How is the degree of dissociation of a weak acid found? What do we say that was? How is the degree of dissociation of a weak acid found? Do you remember? Try to find mine. Oh, I left my notebook over there. What do we call it? Do you remember? We called it flip back. It might be easier for you just to flip back. All right? Instead of me just telling you. You might remember it better. It was degree of dissociation. There's some Hasselbalch.
Is that one where we use the formation of each?
We had a symbol for it. It's too far. There it is. Oh, there's not enough page numbers. The new version has page numbers, sorry. Can I just hold yours up? I'm getting page numbers on this. It's day 26, right where we end up talking about formality. It was X over F. Right? Okay. And then you see where all this stuff is coming from? X comes from the ice table, right? So you write your Ka reaction. They say, oh, the formality of HCN is 0.23. What is its degree of dissociation? So you'd write the Ka reaction. You'd find ice. Sorry, do ice. You do ice. You find X, and then you substitute it in down there. Whatever you get for X, your hydrogen ion concentration. Divide it by your formality, and that's your degree of dissociation. Okay. It was just a step beyond finding pH, I guess, of a weak acid solution. Then we talked about dissociation of water. Right? You can't stop it from happening. It's temperature dependent. It doesn't happen very much, but to a small degree. And we had questions like 1.23 molar KOH. Oh, here. No. Name every ion in this solution, regardless of its concentration, then describe the source of each ion came from. Okay. What ions do we have in a 1.23 molar KOH solution? We have potassium ion. We have hydroxide. What else do we have? Anything else? H plus. Any other ions? Okay. Where does the K plus come from? Yeah, this 1.23 molar KOH solution, right? Where does the hydroxide come from? Yeah, the same solution, and water to a very small degree, though, right? But it comes from both of those. Where does the hydrogen ion come from? Water, and solely the dissociation of water. Okay. What is the concentration range where a systematic treatment would have to be used for this system? Like I said, calculate the pH of this KOH solution. You don't want to see. Good. If you have KOH in that range, or any strong acid or strong base, it's not a simple question. You have to do a full systematic treatment, because now the contribution of hydroxide and hydrogen ion due to water dissociation is appreciable. You can't just knock it off. Okay. How about, I think we got the idea there. Do you want to try that again? Name every ion in this solution, regardless of its concentration. Okay. 1.23 molar sodium fluoride. The ions would be Na plus, F minus, is that it? Has to be ions. Well, NaOH can't form a strong base anyway, but is that it? All right. If you have F minus there, you're gonna really have HF. Well, that means you have this K. Pick your demon, either Ka or Kb reactions going on. Yeah, you're gonna have OH and H. Right. Well, you should write HF as a species, but they want to know ions, so I guess I left it out. So where does this stuff come from? The sodium definitely comes from the sodium fluoride solution. The fluoride comes from the sodium fluoride solution. Hydroxide comes from water. Hydrogen ion comes from water. Buffers. Out of all the buffers listed in the table, how do you choose a buffer for any particular application? By the pKa. You want I want a buffer at pH equals 8.6. Well, then you look through as Google, do whatever you can to find the pKa that's as close to 8.6 as possible. And why? Why do you choose buffers in that way? Should answer. Yeah, the buffer, if you add a strong acid, the conjugate base reacts. Add a strong acid, the conjugate base. Strong acid, the conjugate base reacts. Strong base, the conjugate acid reacts. But how do... You're right, but why do we choose them in that way? When the pH equals the pKa, with, like, you can see this equation right here, how do you get mathematically pH to equal pKa? Yeah, make these 1 to 1. The log of 1 is 0. So pH equals pKa. Why do you want these the same? Because if life is random, if nature's random, you don't know whether base is going to be added to your buffer or whether acid is going to be added to your buffer. So this way you have equal populations of both. So you're about as safe as you can possibly be. You have equal populations of conjugate base and conjugate acid. That's why they pick pH equal to pKa. How do you prepare a buffer? For example, 250 mils of benzoic acid at pH 4. We don't need to write it all out, but how would you do it? Or we can write it all out if you like. Oh, we need a concentration of this, don't we? How the heck? Of 0.8 molar benzoic acid. How would you do this? Do you care? Because they want, all that work is gone through. Someone has chosen benzoic acid, so it must be in the 4, must be in the buffer region, must be really close to the pK. They just want you to make the darn stuff. They want you to make 250 mils of 0.8 molar benzoic acid, and then they want that pH to be 4. You got to describe the steps, figure out how many moles, figure out how many grams, right? Use these two, right, to get the number of grams of benzoic acid, right? To mass out on a balance. It can be a liquid. You can mass out liquids, right? And how do you know what? So 0.25 liters times 0.8 molar, you get the number of moles. How do you go from moles to grams? Molar mass. And how do you know what the formula is of a lot of these funky weak acids? The table, right? You don't have to memorize this stuff. This is going to be in a table. So if you're not sure of what aziridine hydrochloride is, you just go look at the table and see what the heck it is. Okay? So you mass out the number of grams. Put it in. How much water would you put it in? Yeah, okay, put it in a flask, but add, I'm just literally saying, how much water would you add? Just enough to get it to dissolve. And you know what, when you add like DI water, it's slightly acidic, so it will adjust your pH. So you want to add a good amount, the majority of the water, like, I don't know, 225 or 220 or something. Add a majority of the water. I guess, right? And then you would what? Would you fill it to the mark right away? You have to adjust the pH, right? Adjust the pH to 4. With some strong acid, strong base solutions or something. And you miss it, you go add some acid. Went down too far, add some base. Until you find, because all you're doing is just messing with these populations. You're not screwing up the buffer, you're just messing with the populations until you get it the population ratio to where the pH is 4. Okay, just pH to 4. Once it's done, then you fill to the mark. Or, adjust the final volume to 250, whatever the case is. What is buffer capacity? The range. If the pKa is 5.5, let's say this is my pH scale. What is that range? Right? I want how far can I go in each direction before my buffer is not really working anymore? Does anyone know? It'll be 1 pH unit this way and 1 pH unit that way. And then roughly you're done. You're done for. So 6.5 to 4.5. So when you're picking a buffer, right, the closer the pH is to the pKa of that buffer, great, but it doesn't have to match it exactly. But definitely don't be outside 1 pH unit. It's not going to work. Okay, that's one idea of buffer capacity. But then here's another aspect of buffer capacity. More concentrated buffer solutions have a blank buffer capacity. Think of it this way. If it's more concentrated, well, I'll just have more conjugate base, I'll have more conjugate acid. Well, then I can react with more added acid or base. So that's another aspect of buffer capacity. Just make the thing more concentrated. It's not going to help with the plus or minus 1 pH range, because once you're out of that range, you're done. But if you are inside that range, it'll have a higher capacity. Okay. And again, why? Because then you'll simply have larger populations of conjugate acid and conjugate base. Okay. So circle all the names. You don't have this. I added this. But circle all the names of all the buffers that exist as A-, the conjugate base, when placed in water. So I'll number them. You don't need to write all this out. You just write down the numbers that exist No, I added this. So you just write down the numbers. You're looking for all of the buffers that exist as A- when you put them in water. So you're putting in aspartic acid. You're putting in benzoic acid. You're putting in benzylamine. You're putting in boric acid, right? Which one of these are going to correspond to the conjugate base form? Now, this is going to be a really basic solution because it's all conjugate base. It's a good observation, right? But doesn't always work, though. I don't think it always works. We'll see. It might. Let's try it. All right. So did you circle number 1? 1 is kind of a bad choice because it's got 3. It's got 3. So technically there's 2 more acidic hydrogens. So to make this question really work, that was not shouldn't be part of the question. Would you circle number 2? 0D. To make it neutral, you have to lose that hydrogen. So you definitely should have circled number 2. So we are looking for bases. Because to make it a base, you have to lose that acidic hydrogen. Sorry, to make it neutral, you have to lose that acidic hydrogen. So would you circle 3? No. Would you circle 4? No. Would you circle 5? Yes. To make that neutral, would you circle 6? Yes. Yeah. It's another way of saying which ones are the neutral form, right? The conjugate base form. Would you circle 7? No, because the neutral form is the acid form. Circle 8? No. Circle 9? I don't see any plus on 9. There's no pluses here. So that means the neutral form is the acid form. There's 2 of them, but neutral form is the acid form. Okay? How about the rest of those? 10, 11, 12. I think Albert's idea is right. If it ever says acid, I don't think that's hard to prove wrong, is it? Yeah. Yeah, if it doesn't say acid, then you got to look at it. Yeah, so how about 13? That's about the only one, right? Okay. Would dissolved cyclohexylamine react with NaOH or HCl when in water? HCl? Good. Very good. And then we're back to the questions that we've been working on for the past couple class periods. Okay. So, pick your demon.
Are you going to send us or give us any more prompts to do?
I can write up a gazillion of these. All right. I don't have the answers. What's that? So, oh, yeah, we need to see it. There it is. And then I can fix your quiz while you're working on that. That bloody nitrogen.
Cyclohexylamine hydrochloride. That's the neutral form.
Be at 22. Hold. Cyclohexylamine.
Even though I'm confused because we worked it as an acid or base.
Okay, so cyclohexylamine. This, right? The name always corresponds to the what form? Neutral form. So is this neutral? If it isn't, you got to make it neutral because that's what the name corresponds to.
Okay, so the cyclohexylamine is not neutral.
The name always corresponds to the neutral form. So therefore, the name does not correspond to that form. The table is built so it always shows you HA or A minus. Look at all those blue H's. The table is built so it always shows you HA or A minus.
So even
The table is built so it shows you which form. Look at all the blue H's. Every single form has a blue H. This is HA in the table. Is that the name of the, is this the name of that? No. The name only corresponds to this structure if this structure is neutral. So their structure is always of this acidic form. They want to show you where the acidic hydrogen is.
So what they're saying is that benzylamine that's written right there, even though it shows me a structure with an H plus, that's not the real structure. The structural, it would be just.
This is the real structure of the acid form. But is this the structure of what's in the bottle that says benzylamine on it? No, because that can only be a neutral form.
So would NH2 be what's in the bottle?
NH2 is what's in the bottle. So benzylamine acts like a conjugate base, right? And that's going to be NH2. So when you find the molar mass of benzylamine, it has to be NH2. And that's going to be moles minus, yeah, because you know the moles of the base. Okay.
So, and then when you add hydrochloride, it's the acid.
I'm sure this will be super simple.
So if you want to adjust the pH of benzylamine, first you have to recognize, okay, is benzylamine an acid or a base? Benzylamine is a base. So that means you have to add HCl to it. So then when you're adjusting, you're doing this math equation, all you have is base. And that amount is going to go down because you have to add HCl to it. So you're going to have your number of moles of base minus X, and just X is going to be on the bottom.
Okay.
So try it.
So the second one, we have acid and we're adding base to it,
So
right?
the first, yes.
Cyclohexanidine hydrochloride?
Well, let's make sure everyone agrees with this first one first. All right? So what are you going to add, the HCl or the NaOH? You're going to add HCl. Good. Let's circle that one. You're going to add the HCl. Okay. And what are you going to use as the molecular formula? Right? Because they have so many grams. You got to get into moles. C6. 2, 4, 6, 8.
H15. Yeah, 4, 6, 8. No, C6H12.
What about the hydrogen?
Don't forget there's an H right here. Right?
But when the C is in a cyclorene, it already has 2 bonds and can only attach to 2.
Hang on. Is this an aromatic? It's not aromatic. So each corner has 2 hydrogens. Okay? In cyclohexylamine, you've got C6, H2, 4, 6, 8, 10, and this is 12. Shouldn't it be 13? Right? I can write them all out, but remember you're going to lose one of those H's. You're going to have NH2. C, H, CH2, CH2. Yeah. I see how I suck at drawing these things. I already lost my spot here. The C6, H13, N. Right? One more carbon? One, two, three.
That's cyclopentane.
That's, yeah, I needed 2 more. I guess get ugly this thing. See, that's why I hated organic. I suck at it so bad. Write them on here. It's a lot easier.
But since it's the amine structure, we're looking at an NH2 at the end.
Yeah, and let's just change that to an H2. Right? You got it? 2, 4, 6.
Name always correlates to the neutral.
We got an H right
99.
there. Okay. Okay. So you see how to start that one? How about the, let's erase this. Let's do the molar mass. Let's get started for number B here. What would be the structure? Would you add HCl or NaOH first for part B? You would add which one? The cyclohexylamine hydrochloride,
So then that
NaOH. Because this guy, he's so much easier to draw the structure of, right? That's all you got to do. So you're going to have to add NaOH, right? And then the structure for this is a lot easier to figure out. C6, H what? 2, 4, 6, 8, 10. Should be 14, right? H14, Cl. Oh, gosh, my goodness. Right? That's a chemical formula to find the molar mass. Yep.
So that one's just like we did on the quiz. So on the ice, the number minus the x will be on the bottom.
Well, if you're not sure, you can just write it out. You know that this is going to be a conjugate acid.
Yeah.
So don't write the structure out, just write HA.
Yeah, I was just saying about these.
And then you can do ice on them. That way you don't screw up with numerator and denominator in Henderson-Hasselbalch. I think it's kind of safe to write this.
So when it has the hydrochloride after it, it's going to be considered a base, an acid?
Pretty much, I'd say every single time,
Okay.
right? I really think so.
So that neutral form right there for the cyclohexylamine hydrochloride, that's actually a salt, right?
Yes, it's going to be a salt. Because you have a cation and you have an anion.
And we're just assuming, well, I guess.
It could be.
It's a salt. We just know that we want to use the acid, the conjugate acid there.
God bless you.
You just, what do you mean you don't know it? You just look at the table, it tells you. To make this a chloride, right? Here's my cation, there's my anion. That makes it a neutral compound. So when I dissolve this in water, I'm going to get a lot of this and a lot of chloride. You don't care about the chloride, it's the conjugate base of a strong acid. It's not going to do anything. This is going to do everything. And what is this? It's a conjugate acid, right? Wow. You guys got extra bang for your buck today. I don't have anything else to do if you want to hang out longer, though.
Can you come up with the quiz answer?
Yeah.